It's working. Okay, so what we're checking out right now today, right? This is the one quick review on what we left off last time, introducing Gibbs free energy, delta G naught, and other components sort of associated with that. Really, the most important thing with that, we're talking through a series of different ways of looking at this projection, right? This is an example of two important things we're expressing, right? So first of all, there's this quantity we talked about here. This is our starting state. This is what we call our starting materials. In this expression, we're describing the extent of reaction. So if we had some theoretical reaction, starting material turns into products, this is describing all of that starting material, whatever we describe on the left-hand side, turning into all of the products, whatever's on the right-hand side of whatever expression we're describing. This 100% gap here, we call this delta G naught reaction, right? That is the overall part where all starting material turns into all of products. That is, think of that as a quantity which is based on the energy of whatever is at these two extremes. Now, how would we read this? What are we interpreting, or what are we saying about this reaction? If the delta G naught is positive, what does that instantly mean? That simple fact, delta G naught is positive, there's a bunch of other things that we suddenly can start to conclude about this reaction in terms of what's more, okay, we got endothermic, we got non-spontaneous. Yeah, I'd say definitely non-spontaneous is correct. It will not spontaneously take all of this starting material and make all these products. Let me drop on endothermic. Is this endothermic? If I'm representing delta G, what does endothermic mean? Yeah, okay, sorry, let me try to adjust that. Doodly-doo. Is that any better? Yeah? Okay, let's try off that one. Thanks for calling that one in. We'll keep at it, and again, I'll adjust as we go through. I have a couple different options. So if this is endothermic, what does that mean? And needs energy to go. More importantly, what is endothermic? Which parameter are we talking about? Delta H, delta S, yeah, delta H. That's not what we're showing here. Remember, on this screen, what we're talking about here with delta G is made up of delta H and delta S. We can't immediately conclude that this is, the delta H here is positive. What we know is delta G is positive, but that could be the result of either delta H or delta S, right? There's two ways we could get a positive delta G, right? No, I'm absolutely still recording. This is all going through OBS. Don't worry. So, it is an endergonic reaction, we could say. It takes in energy, but we're not going to subscribe it to specifically delta H. What we do know is, okay, non-spontaneous. What about position of the equilibrium? What is more stable, starting material or product? Yeah, starting material. Reactants. Reactants are going to be more stable, not the products. Absolutely. That's exactly what you're seeing here. The other thing we're saying about this, right, the overall change here in this one here, it's a positive delta G naught of reaction. Which is more stable at equilibrium? Or what do you think the equilibrium mixture is going to be comprised of? Is it more starting material or more product? Given that the starting materials are more stable, when it hits equilibrium, yeah, we know it's going to be made up of more starting materials. That's the second thing. If the delta G naught of a reaction is positive, its starting materials are more stable. That means at equilibrium, we're probably going to have more starting materials than products. What does it mean about the sign, or sorry, not sign, magnitude of K, the equilibrium constant? Is it going to be bigger than 1, smaller than 1? Yeah, it's going to be smaller than 1. We're saying that the product concentration will be small relative to the starting material concentration, which means less than 1, right? So the important thing I want to sort of tag on there is there's two different things we're describing. Delta G naught of a reaction, or K, or saying that the starting materials, something about, sorry, maybe not starting materials, I'm going to say relative stability of starting materials or products. These three things sort of describe the same thing. In other words, if the delta G naught of a reaction is positive, that immediately means that K must be less than 1, which also means starting materials are more stable. These are also synonymous. In other words, knowing one of those factors, all other are true. You could, if we told you K was less than 1, the other two parts are also true. If we say the starting materials are more stable, now you know something about K and delta G. Okay, so the point I'm trying to make there is these three things, saying them these different ways, are really talking about the same property. It's describing, it's describing this. It is describing an energetic diagram focusing on where the starting material is and where this product is, and the relative height or change between the two, right? So they're different ways of describing the same phenomenon. At the same point, if we made the corollary, if we said that this was negative, then that must mean this is going to be greater than 1, which also means that my products are more stable. Okay? Again, all three things are synonymous. So the important thing with this is you can get the same information by any one of these three pieces, and you must make sure that there's a transitive property to the other two. Knowing one thing tells you the others. When you see what I've written out here in blue, you know, a positive delta G, K less than 1, as soon as you hear any of that, the thing I want you to snap into your head is you're looking at, mentally, this is the diagram that's kind of popped into your head. Less than, positive, there's your delta G naught. That's what the piece that really matters is you kind of bring these together, okay? The next thing we talked about was delta G reaction, not delta G naught. Delta G naught, remember, is the single value talking about all of this going to all of this. It's where this kind of the ski hill looks like. It's the energetic surface. We talked about Q and delta G reaction. Those are talking about where you are on this ski slope, right? Well, if we said that a specific part, as we travel from 100% starting material to 100% product, we have different values of delta G reaction, of where we are on here. So in other words, if I was standing right here at this point where my cursor is, on this part of the hill, remember, that's like parachuting in, you're standing on this hill, your back is always towards starting material, your face is always towards product. If I'm standing here and I wanted to move towards product, is that uphill or downhill from this point right here? I got to go uphill. So if I had a composition, a reaction mixture right here, am I at equilibrium right here? No. Is it spontaneous to move towards product, make more product from this position? No. What does that mean about the sign of delta G when I'm standing here on this hill? Yeah, it must be positive. It is not spontaneous to move towards products. It is spontaneous to walk backwards downhill. So delta G tells you where you are on this surface. Delta G naught tells you what surface you have to deal with. Okay? Same thing with K. K says where equilibrium is. It's a fixed point. Think of it as a geographic location. Q says where you are on this continuum towards these other points. Are you at equilibrium? Are you ahead of equilibrium? Or are you behind equilibrium? Delta G and delta G naught tell you the same thing. Delta G naught tells you what the surface is. Delta G says, am I at equilibrium given some surface that I have to play with? So right here at this minimum, what's the sign of delta G if I'm standing right here at this little minimum part? That's 0. That's like saying I am at equilibrium. While I'm sitting at equilibrium, what's the value of Q? Q equals K. And that's why I've got these other two parts over here, right? I've got Q ahead of K or Q behind K. And remember, that comes down to, since they have the same equation, products over starting material, if Q is bigger than K, too much products. If Q is smaller than K, too many reactants with respect to the equilibrium position, okay? So let's go back to the iPad. Delta G and Q, these guys say where you are on the energy surface. think of it as a reference point. So starting off, if what we had was free energy and extent of reaction, right, where this is all starting material and over here is all product, we've got those two sort of pieces. First thing we're going to say is, I'm going to come up with something hypothetical, not the one we just did. First statement we make is, it can be any one of these three statements. We need to make one of these three statements to make a definition of what kind of surface we're dealing with. What's your sign of delta G naught, or your K, or the stability of one of your materials? So let's say, in this case, I'm going to say that for this reaction I'm considering, for some hypothetical reaction, the delta G naught of that reaction was a positive value. Actually, let's do it different. That was what we were just describing. Delta G naught is a negative value. Instantly in your head, you go, well, that must mean I have a starting material, I have a product, and it must be some drop in energy. That's what I'm saying here. That's the value I've done. But what it means also is products are more stable. The K value must be bigger than 1. Other two things snap into focus as soon as this statement is made. It also means the energetic surface that connects the two will look something like this. It's an ellipse or a loose line that connects the two where there's going to be a dip, not at 100% product. It will be close to there. It's closer to product than starting material, but it's on that way. That dip is how we represent our equilibrium point. That is the point where delta G is equal to 0. That's also the point where Q equals K. The reason why these things matter is, remember, they are specific indications along this energy surface. As we walk through this energy surface, Q, or delta G and Q will change, right? Delta G and Q will change as you move between the surface. So we use those values to say where along this surface I am. The surface will change, or what shape it takes on comes down to this first definition of who's more stable. Endergonic and endothermic, these are not the same thing. So first of all, endo versus exo. What does that mean? If I said endo, what am I talking about? The direction or movement of energy in or out of a system. Yeah, endo means in, exo means out. Just on that part, just the word. Endo and exo is a direction of movement of energy. Thermic specifically talks about heat energy. So endothermic means gaining or bringing in heat. Exothermic means releasing it with respect to the system. Endergonic talks about bringing in free energy. Exergonic, releasing free energy. So something with a delta G naught negative, that is an exergonic system. That's the definition. Everybody cool on that one? Okay. All right, so that's the first part I wanted to make sure that we kind of touch base on. This graph has two components. There's really, the last one, exergonic. Oh, sorry, let me write it down. Doop. Doop. So delta H positive is endothermic. Delta G positive, we say it is endergonic or endoergonic. This term, ergonic, is just a general one for energy. Exergonic means the energy leaving the system, exactly. So the point here, this graph has two major components and a lot of corollary statements. Delta G naught, K, or stability of starting material product, that's the overall shape of this curve. Q, or delta G, says where along this axis or continuum between starting material and product is, right? So that's how we divide these guys up. Okay, for today, for this one, I want you guys to tap into the chat for your answer. For this reaction, what is the delta G? For this reaction, delta G naught, positive, negative, or equal to 0? Awesome. Yeah, absolutely. This is a case, remember, you measure, and when we say look for a specific point, this is something that no matter what this tie line is, we don't have to indicate a specific location. Delta G naught has one value, which is given by the drop between these two. We could say that in this one, if I start with 100% A, so this is starting to have language that describes a particular location on this surface. If I start with 100% A, what is the sign of delta G? Positive or negative? 100% A, is it positive or negative? Yeah, picking up, we're getting a lot of negatives, so maybe some positives. Remember, in this language, if we start with 100% A, what is the sign of delta G? There's two things there. This tells you where to look on the graph. 100% A, in this reaction, A goes to B, that's right here. That's at the starting material, which means I'm standing right here. Remember, as far as figuring out the sign of delta G for this reaction, you stand right here, you put your back to your starting materials, your face to the products, and you say, I'm on this point right here. Which way is the slope? Am I downhill or uphill? So if I'm standing right here, this is top of the ski slope, right? You are on Grouse Mountain. You've just put on the double diamond thing. You're about to jump down there, and you don't have ski poles. You're just going to go for it. That is a negative slope, probably a negative experience too. But yes, right here, at this point, it must be negative, which means, what does that mean about spontaneity in terms of moving towards product from this location right here? Yeah, that'll be spontaneous. It's downhill. So point is, when you're describing things about Q or delta G, there must be some reference about where on here I'm going to be describing, more towards starting material or product. Here we're saying right here at this 100% starting material, or just when the thing mixes up, that's going to be there. So it'll be a negative delta G at that point. Where, on this case, is delta G greater than 0 or positive? Yeah, that's a good way to describe it. After equilibrium. That's good. This is a lot easier if you can point, right? So right here, right? In the part of the curve or the composition of this reaction after this equilibrium, and again, that's referring to moving from starting material to product as like 100% starting material to 100% product. As we move across here, this region right here, we'd be walking down, 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 down. Oh, delta G equals 0. I'm happy. And then as you continue to move through that, here, delta G is going to be positive. So it's anywhere ahead of this equilibrium position, at least with respect to the forward reaction, right? So now we're going to put this in terms of actual sort of calculation. What we want to do is calculate the ratio of these products. So this brings together the same concepts we did, but it's going to bring together some of the equilibrium equations that we talked about up until now. So does anybody recognize this molecule, first of all? Do you know what this thing's called? This kind of like bow tie looking, looks like a Budweiser symbol. What is that? It's not a sugar. You're right. It does kind of look like a hexose. That's true. Usually hexoses have oxygens in them. This is what's called cyclohexane. It's a cyclic molecule. Hexane, there are 6 carbons. We're going to get to know this a lot when you start playing into the organic section, for sure. Yeah, this is cyclohexane over here. Cyclohexane has 2 what are called conformers. Over here, this is one way of drawing that molecule. If I take this methyl group, the CH3, I can have it presented in what's called the axial plane or the equatorial plane. Think of these two. This is an interconversion between 2 geometries of a molecule. And if you're given the information that this molecule here is 7.5 kilojoules in mole higher in energy, that is an indication of what? What is this telling you? What is that information telling you about this system? Who's more stable? Well, not thermic, again. Yeah, okay. Higher in energy, though. The left is more stable than the right. Okay, so that is exactly how I'd look at it. The starting material is more stable. What you're saying, this number here is saying, from here, I must go up in energy by 7.5 kilojoules. I'm climbing a hill to get here, right? So what that means is, again, with that piece of information, here, let me put it up here this way. Wait. Oh, no, I think that worked. Can everybody see kind of both? Sort of. Oh, no, it's totally messed up. That sucks. Hold on a second. Bloop. Bloop. Yep. Oh, well. I will get that part fixed. Let me just kind of do one of these for now. All right, point is, at this point in time, when we get this up and running, you're kind of saying, I have what we're going to call my starting material, and I'm going to go to my products. That's just defining by saying I've got something on one side and I've got something on another. If I said this is 7.5 kilojoules per mole higher in energy, what I'm saying is this diagram should look like starting material, product, and what is this value that I'm saying higher? Of the things we just discussed, delta G naught. Yeah, this is a numerical value saying starting material to product. This is delta G naught. It is the change in energy from starting material to product. And we just said it's 7.5 kilojoules higher in energy. It's only this. What does that mean is the surface that I would be sitting on would look like what? If I had to sort of verbally describe what would this look like, where is my K here? Bigger than 1, smaller than 1? Based on what we just figured out, delta G naught, yeah, it's going to be smaller than 1. Why? Because starting materials are more stable than products. It's going to look like one of those cases where it's dipping and then up here, right? So if this is, again, 100% here, this is my extent of reaction. If I have that across this axis, this is 100% starting material. Over here we have 100% product, and going up in energy is here, which means the value here is where I'm going to find my K value, right? Or this, actually, on this graph, what I'm actually indicating there, this is my equilibrium point. Right here, delta G is equal to 0. That's my equilibrium position. So that first statement of amount of energy puts all these other things into concept. It also says that one of the two things is more stable, starting materials. Cool. All right, now let's quantify this. What we need to do is calculate the equilibrium ratio. What we're being asked now is to say, okay, if I'm going to have to calculate an equilibrium ratio between these two, which is correct? How do I calculate this equilibrium ratio? How do I put a number to this? We've got a qualified value, right? We know that starting material is going to be more stable. So the ratio of starting material to product, all of these say starting material will be bigger than product. That's cool. But how do I get a number? What equation do you remember that relates specifically delta G to K? Right? K is products over starting materials. That's right. We need that. But yeah, the equation that actually puts those two together is minus RT ln K. That's right. We know delta G naught is equal to minus RT ln K. When we're at equilibrium, what is the general equation to? I want to quickly touch on that. What was the more general equation? This one is what applies when we're sitting at equilibrium. What's the other equation which has Q in it? Delta G is equal to delta G naught plus RT ln Q. That's the reaction quotient. So one thing that happened, we brought up last time, an error in that point. Yeah, sorry, this is the delta G naught. We mentioned that at least there's a certain embodiment of this equation where there sometimes is a molar value, an N value in there. That value should not be there. This is, on the slides I presented last time, this is the correct equation. The value for N there is a specific instance that we can use under a certain point. We will be using this embodiment, this equation. This is the general expression of it that you will use for your calculations. In other words, if you need to find out a specific delta G value, given a delta G naught, you just need to know an equilibrium ratio of your Q to complete this. Okay, so just to clarify that. So there's no N. Okay, this is what we're going to use. We have a delta G naught reaction. We have minus RT ln K. We don't know K, so we need to solve that. We just need to come through and measure and solve our K value. Okay, that's not too bad. So we got delta G naught of this reaction, and we said that's equal to 7.5 kilojoules per mole. Cool. What else do we know? We have to get delta G naught equals minus RT ln K. Yeah, we've got temperature. Cool. Yeah, temperature here, that's 25 degrees Celsius. What's the R value you want to use? Yes, this is definitely still part of the midterm. We can still practice this point. It's 8.314, right? Cool. What about units? 8.314, what are my units for that? That's joules per degree Kelvin.
I actually don't think this is part of the midterm. Sorry to interrupt, but on that email, it only said we're going through like delta G reaction, but we're not doing extensive reactions, I don't think.
I'll double check with Professor Strichek, but good info anyway. Again,
Anyway,
the best
sorry
is,
to interrupt.
no problems whatsoever. Now again, the best way to look at it, right, is based on the practice midterms that you've got. Those are sort of the target questions you should be into. But again, don't worry, I promise I'll clarify that part. Definitely not the Van't Hoff stuff, but we'll sort of finish off onto today. So 8.314 joules, Kelvin, mole, right? So does this look good? If I just kind of cram all these numbers together, is this all going to work? We've got delta G. No, what's wrong? Okay, yeah, joules, kilojoules. There's one more problem. Yeah, temperatures in Kelvin here. So make sure you convert the two. If we bang this part out, this is going to be 7,500 joules per mole, right, is equal to minus 8.314 joules, moles, Kelvin. All of that is multiplied by 298 degrees Kelvin. Now we can solve for ln K, right? And if you push all this part through, what you'll work out is K, right? It's the inverse log of this value, or ln K here would be equal to negative 3.03, or K is equal to 0.05. Are we done? Can we look back at this and say, oh yeah, I can pick a ratio from this? Why not? Yeah, no, not yet. There's one more step that's really, really important. I just want to emphasize this. This is the value of K that we solved. What is the equation? K is showing you what? K is equal to 0.05, which equals what? What do if I had to draw the equation, yeah, products over reactants. It's product concentration over reactant concentration. The value that's represented up here, the ratio, a ratio, right? You can think of a ratio as it's synonymous with like a percentage, right? It's some amount of product out of 100%, or you can think of this as total. The total quantity of material in a system. This is not total. This is two molecules, concentration of something else. That is a fraction of two different pieces. Here, percentage is products over all of the stuff in the system. That's how we get to a value out of 100, right? K here, as it's represented, this is like saying products is equal to 0.05, reactants is equal to 1, right? So that means total here is equal to products plus reactants. If I had to sort of convert it through, the ratio in this case, or percent value, would be given by 0.05 over 1 plus 0.05 is equal to, in this case, mathematically, it's pretty close, 0.048, or approximately still 5% of the overall system. The answer in this case is still this 95 to 5. Sorry, what was it? How do we get the 0.05? 0.05, this value for K here, that comes from our calculation. Certain amount of energy, RT ln Q, solve for K in here. Yeah, e to the ln K value, exactly. 8.314, that's R, dude. Whoop. Okay. So in this case, we work it out. This is still a 95 to 5 ratio, but the thing I want to emphasize here is K is specifically this, right? K is products over reactants. A ratio with respect to 100% is amount of material relative to total. That's sum of both two. These are not always the same thing. In this particular numerical case, 5% is close enough within error that you would still get the right answer. That's not always the case though, right? This is something that there's a differential between these two. So I just wanted to emphasize that. Okay, so the last thing we're going to discuss through. Last thing we're going to discuss through here. Sorry, and slide that back up here. Yeah, I know. So, of these three, which of these graphs represents a weak acid dissociating in water? Yeah, absolutely. I agree with that too. C. So this goes back to the first thing I was saying. Making a statement about which species is more stable, something is more stable than something else, what you're saying there really is that there is a sort of a consequence to your delta G naught value. And what we know from weak acids is they have what for values of K? For a weak acid, one of the definitions of weak acid was what? Yeah, K is less than 1. Remember, of these three, the only one of them where K is less than 1, right here. K of less than 1 is at this point right here. This, K is greater than 1. What's this one? K equals what? Yeah, this is K equals 1. So, having something about, knowing about a stability or stability of a system immediately invokes one of these three kind of graphs that you should be familiar with, right? This guy over here in particular, this is the case where this is K equals 1, this is K greater than 1, this is K less than 1. At equilibrium, delta G equals 0. Delta G naught is always this differential value. This is the point where we're at equilibrium. This is the overall energy difference given a certain system. So that's why I think of the two. Delta G naught defines which playground you're on. Delta G says where you are on that playground. For all three of these, there is a point where delta G equals 0. Here, here, or here. They're in different positions depending on which surface you're on. Delta G naught tells you which of these three surfaces you're playing with. Make sense? All right, cool. So the last thing we have to discuss is, again, quantification, or how we go back. This is the final sum of all of the equilibrium and all the thermodynamics we've done. Remember, we talked about delta G naught has two different equations that we've now defined. The first one, remember, that goes where we're starting to fuse together the first law, the second law, the third law. That introduces this concept where delta G naught is equal to the exothermic or endothermic term, and then also your entropic term. So enthalpy and entropy. Quick reminder, quick question. Give me one way using calorimetry to calculate or measure this value. What would I do, or what's related to calorimetry to get me this delta H naught reaction? Yes, constant pressure. Yeah, heat capacity is involved, but it's a constant pressure measurement, which is the heat. We call that what? Q sub, yeah, QP is our value there. That's our thermicity, right? Okay, so next, that's our thermic value. This is our entropic value, right? Quick thing, give me one example where you would expect delta S for reaction to be massive and positive. What's one example where you expect the delta S to be huge? Explosions, combustions, yeah, but what else? What's a phase change? Did you say like that would be a very big number for a phase change? Yeah, sublimation, that is a great one. Solid all the way to gas, that's a huge one, right? Or producing gases in general, that's right. Okay, so this is our general term we use that relates our delta H and delta S. And from that too, like we've just been discussing, these are great values because this tells you about the heat in the system as change in bonds. This tells you about the order in the system. These are very useful thermodynamic parameters. We can use Hess's law. We can use standard entropies or enthalpies. These are ways to access these, but a lot of the times, what we actually have is actually measurements of delta G. That's what we just did here. If I have a system in equilibrium, like we just did in the last example, up here, I can actually put these two things in a system and measure the ratio of product to starting material. Measuring 95 to 5 means this is less stable, and it's less stable by 7.5 kilojoules. The simple ratio of the two is a really easy way to measure K, and if I can measure K, I know delta G naught. This is a really good thing for us to do experimentally. So sometimes what we actually have is K. Temperature is easy to measure. K comes from concentration, so I can actually measure delta G naught pretty easily. It's not always easy to measure delta H or delta S. So what we want to do is squish these two things together and say, look, here's one equality where delta G naught equals minus RT ln K. Delta G naught also equals delta H minus T delta S. So I'm going to equate these two equations together. This guy equals this guy because we have a common term over here. They're both equal to delta G naught. So pushing them together, I get this new one. Minus RT ln K, that's our expression here, equals delta H minus T delta S. That's just our first one over here, right? This is just expressing those two ones we've talked about. We're going to make one more assumption. In this case, provided delta H naught and delta S naught do not change with temperature, if we assume they're a constant, again, that is usually a pretty good assumption for sort of normal, what I'd call to, a couple hundred degrees Celsius. That's okay. Astrostellar, things get kind of weird under some systems, but this is a safe assumption. What that does now is if these guys are constants, we now have one equation that relates temperature, K, R, to these two very valuable thermodynamic parameters. All I'd have to do is measure K at some temperature, and I can extract these two values, potentially. So this is what we call a Van't Hoff plot. If I start off here and say, look, minus RT ln K is equal to delta H minus T delta S, I'm going to solve for K. I'm going to rearrange things and solve for K. So all I have to do, by the power of algebra, divide by RT ln K, or RT on this side, and what I get is this expression. T cancels out over here. So from this one, if I have this now set, I've got my ln K value. If you notice this, the two things that are variables here are my K and my T. I'm assuming delta H naught and delta S naught and R are all constants, right? We're saying that, okay, these are going to be constant temperature. Yeah, this is also at a constant pressure too, right? That at some constant pressure, we're making this sort of assumption or this measurement. But as long as we hold those conditions constant, we now have only two variables amongst all the things on this point, which means if I can extract that, I now have something set up like this. All I'm doing is factoring out the 1 over T value associated right here. So remember, measured value, constants, and this one here is our dependent value. This looks like the equation of a straight line. Y equals mx plus b, okay? What that means now is I have a linear relationship between this here, my y value, ln k, and my x value, 1 over t. So if I plot ln k on my y, 1 over t on my x, I can now extract these two. This, what is this one called? M is your, that's your slope. B is your y-intercept. R is a constant. It means I can now look at a plot of a straight line that was made by ln k, 1 over t, and I can talk about the enthalpic value, the heat, I can know that based on the slope. I can know something about the entropy based on the y-intercept. Those two values on that plot suddenly become super, super useful, okay? So this is what we call a Van't Hoff plot. This is a relationship that Van't Hoff came up with that allowed us to get access to delta H and delta S using only temperature and K, assuming delta H and delta S did not change with temperature. This is super, super useful for things like solubility. Predicting when things is going to dissolve at a different temperature is something we can do quite well with this relationship. It's a very useful kind of one. But it also tells us some basic things about this reaction. So here, if this is a Van't Hoff plot, notice here, this is ln k on my y, this is 1 over t on my x. Because it's 1 over t, big values of temperature are over here, right? It's not, don't read this as high temperature, low temperature. Remember, it's 1 over temperature. So this is high temperature, This is low temperature. Is this exothermic or endothermic? How would I know? If I'm talking about thermicity, what value am I talking about? Delta H or delta S? Yeah, thermic is delta H, absolutely. Okay, so here, let me put this into my link over here. Click here, and we're gonna, yeah, that's good enough. Okay, I agree with you. This is exothermic because let's do different points. We want to know, is it exothermic? Well, what that means is exothermic is talking about delta H, and we're asking, really what we're saying, is it positive or negative? We're asking about the sign associated with delta H. Okay, which value, M or B, from our Van't Hoff, which one of these talks about or describes delta H? M. Okay, so B's off the table. M's what we need. One from the Van't Hoff equation. What was the equation for slope? M is equal to, yeah, negative delta H naught over R. It's this composite. Negative sign is in there. In other words, what is our slope, positive or negative, from what you see here? In our case, slope is positive. That means if delta H were positive, what should the sign of slope actually be? They have an inverse relationship, exactly. In our case, if slope is positive, that must mean delta H is a negative value, so negative multiplied by a negative would give me my positive slope. If my slope is positive, my delta H must be negative. If my slope is negative, my delta H must be positive. And that all comes down to, this is the equation for our slope. They're inversely related. So yes, this is an exothermic plot, an exothermic reaction. Very good. What about this dude? Endothermic or exothermic? Yeah, slope is negative, therefore delta H must be positive. Right, this is an endothermic plot. What about this one? Entropy, based on what I gave you here. Is the entropy positive or negative for this reaction? Okay, we're getting some positives. Are you how do you know that? What value do you go to? So here's our plot. This is our ln k. Here's our 1 over t. We've got a slope, a line here, and I totally agree with you, right? M here is equal to a negative value, therefore delta H is some positive value. It is exothermic, or endothermic, excuse me. Yeah, delta S comes from B. That's right here, right? This is my B value. What was the equation for B? B is equal to, yeah, delta S over R naught. Yep, good. Okay, but look at this graph more closely. Where's 0? Is B positive or negative here? Are you sure? This might not be 0. What if this was minus 50 and up here is minus 10? The point I want to make, this is a representation, and in fact what I gave you here was not a Van't Hoff, that is a Cant Hoff plot. You cannot tell. There is no way to know the number for B given the information that you had. I know, sorry. It's a Cant Hoff plot. Oh, come on, it's Friday before the midterm. It's totally fine. You get that. Anyway, point is, take a second, look at the graph. If the information's not there, it's not there. The other thing I want to emphasize too is I'm a kineticist. I do a lot of things by graphical manipulation. There's nothing else that ticks me off more than unlabeled axes, right? This is not cool. Sorry, that should be 1 over t. So numbers matter, right? The reason being is sometimes, actually, like I've created Van't Hoff plots before. Because of the axes that you typically deal with, you often will actually compress this. If I actually were to do a real Van't Hoff and it looked like this, some of the times, if I actually put an axis like this and said here's 0, my entire Van't Hoff would be like that. Right, so the problem is usually what we have to do is focus on a zoomed region of the axis in order to express the information we're dealing with, just as a one-off mention when we actually get to real data. Okay, sorry. I'm sorry, that's one of my favorite many jokes in this one. Point is, if you go through this, right, so in this Van't Hoff plot, A, B, or C, where does entropy, where do you get entropy? This one everybody should be able to get for sure. Right, entropy comes from the y-intercept. Slope tells you about the enthalpy of this system. Positive or negative tells you sign. X-intercept, what's that one for? Just fun. Yep, we don't typically use it. You can extrapolate it back, or you can still get equations of straight lines from it, but it's not related to our thermodynamic values. So using this numerically, the last thing we can go through here is that, look, I've got a numerical value, an equation, a best fit for a straight line. So what I'm going to do now is actually extract the numerical values for h, or delta h and delta s. So if I had a case like this, what I've got is my Van't Hoff equation where ln is equal to excuse me, come on, pen, you can make it 24.71 minus 3965 over t. X-intercept is nothing. That is a fun little game. It is not part of our thermodynamic equation. We don't use it in part of it. Because remember, in the Van't Hoff equation, this is y is equal to m is right here. The 1 over t value is right here. So this is our m value. Over here, this is our b value. And just like we described through, m is equal to minus delta h naught over r. And that is equal to minus 3965. Endothermic or exothermic? No, you use y-intercept. X-intercept is not something we use. Yeah, this is endothermic, right? Negative slope, positive delta H. That's right. So if this is our value here, we just need to solve for our delta H. So again, if I take this through, I'm going to multiply this by, so I'm going to bring R up over here, multiplying this by 8.314 joules per mole Kelvin. My delta H is equal to, and if I wrote this one out, 32.97 kilojoules. So I've done a multiplication here. You take that, multiply it by 8.3, that value is in joules. To convert it to kilojoules, you divide it by 1,000, right? So this is our delta H value. And yes, it's an endothermic quantity. We knew that one based on the slope, the magnitude of the slope that we've got through. Next one, our B value is equal to delta S naught upon R, which is equal to 24.71. We multiply this one through. Once again, we're using 8.314 here at this point. So 24 multiplied by 8.314. This is in joules, mole, Kelvin. Finishing off, we get 205.4 joules per mole. Now remember we talked about before, look at your units. This is a typical thing that you're going to see for certain cases. Enthalpy values are generally larger, generally expressed in kilojoules. Entropy values, smaller, oh sorry, not mole, joules per Kelvin. There's still a temperature quantity built into our one, joules per Kelvin for these two. Point is, when you give an equation of a straight line, make sure you use the right part of the equation and you use the right R value. Using an R gas constant of 8.314 will give you your values back in joules. So this is our overall final calculation, same one I just did at this point here. So that's how you complete equations or analysis using a Van't Hoff equation. All right, that is the end of thermodynamics. That's the end of the material. Again, I will review and we'll put out one more note to make sure cutoff. Again, if as mentioned, I apologize, if as mentioned was up until but not including the extent of reaction point, that's straight. So we will follow whatever Dr. Strichek definitely put out. I just make sure I will mention that and I will double check with you. This last part, the Van 't Hoff one, absolutely. That is after midterm. We're not doing that, but that completes the entropy and free energy discussions that we had. I will hang out a little bit longer. I will post this one up. Thank you guys for sticking with me for the first simulcast. I look forward to see you guys in person next week.